And yeah, thank you, Ilya, and everyone else from NUS for organizing this. It's been a lot of fun to be here this week. It's my first time in Singapore, and I really appreciate all the arrangements and all of you for being here. So I took the instructions from the organizers to sort of give a tutorial-style talk. So it's a little bit looking backwards, like some of the other talks we've had this week. And it's a project I've been working on for about 10 years, but actually I'm still quite actively working on. So if you've seen some of this stuff before, I promise there's some newer bits at the end, and if not, I hope you enjoy it. So I'm a programming languages person by training, and I really have a lot of fun working on designing new abstractions for different kinds of programs that arise in various domains, especially systems and networking. And I'm often inspired by what happened in the field several decades ago. You know, programming languages is an old area, and its kind of major accomplishments got its start way back in the sort of 60s and 70s, when there was all this talk of what was called the software crisis. This is a picture from one of the, I believe, NATO meetings where this term was originated, and a bunch of, sadly mostly men, were working on this problem. And so the problem they were working on was, you know, originally there were these kind of giant mainframe computers, and they were very difficult to program. They had very limited resources. And there was this sense that's captured in this quote from Dijkstra that, well, maybe once the hardware gets a little further along, we have more memory, we have faster processors, you know, programming will get easy. And of course, that's not what happened. Computers did get faster, memories got bigger, you know, there's a lot more capabilities available, but software didn't get any easier to write. And so this famous essay from Dijkstra captures sort of, you know, the problems that emerged, and this led to a big push to think about writing software in a different kind of way. So instead of writing machine code, to have higher level languages, to have things like type systems, to have compilers, and really, you know, all the modern things that we take for granted kind of were set from this initial push. So today, you know, ordinary software we write in languages like Python or Java or Haskell, but there's a lot of systems where we're kind of still back in the dark ages, kind of similar to what was going on in the 60s. And you know, I would argue that kind of the shape of computers has changed. A lot of computations that we write today, they don't just run on a single machine. They run on, you know, large numbers of processors that are sometimes distributed even all around the world. There's a big push for heterogeneous hardware. You know, the end of Moore's law has caused chip designers to think about creating different specialized kinds of units. And then, of course, there's all the challenges with security, which we've not dealt with, and which having large-scale networked and distributed systems makes more important. So for the last 15 years or so, I've spent most of my time looking at how we could think about writing programs for computer networks in a different kind of way that might solve some of these problems. And kind of goes without saying that, you know, networks are a part of pretty much all modern systems. But it's also the case that networks, until recently, have not been very programmable. And if they are programmable, we have to basically write those programs in machine code. So to kind of put this in pictures, this is sort of a cartoon of a conventional network. It's got some elements. These could be routers or switches or other kinds of devices. And, you know, networking has been quite successful as a field. The internet's this amazing kind of wonder of the modern world. But the capabilities of conventional networks are really not defined by the users of those networks. They're defined by things like standards bodies, you know, the IETF, the IEEE, and other organizations that define how these things should behave. And when we program them, we don't tend to kind of write one program that says, give me a network that, you know, does this one thing. Instead, we have these fixed distributed protocols that implement, you know, certain kinds of services, like routing protocols or name services and such. And when these things evolve, it's in a sort of tight dance between the standards bodies, new protocols that people want, and then the equipment vendors who ultimately decide what new kinds of functions they put on these devices. So this is how networks have been for roughly the last, you know, several decades. And the important takeaway is that it's really difficult. If you want to get this kind of network to do something different, unless you can find a way to encode that into the existing protocols, services, and hardware capabilities, you're kind of stuck. And so it's been difficult for system owners to really, you know, think about evolving networks with new kinds of capabilities. So there's this different approach, which in a cartoon way just sort of says, well, why do networks have to be different than, the rest of our computing systems. Why can't we take more of a top-down approach and start with the system owner being able to say, this is what I want the network to do, and then have a whole stack that lets them take those requirements and their specification of what the network should do and somehow implement that in the network. And so there's been a several decades-long push to make this vision possible. It includes innovations all across the stack, so new kinds of programmable hardware, new domain-specific languages, and then all the associated tools like compilers that make it possible to realize those programs on the hardware. And just to give you a taste of some of the kind of motivating or killer applications for this, one of the initial ones was really motivated by large-scale cloud computing data centers, where the companies like Amazon and Google and Microsoft, they wanted to allow customers to bring their existing infrastructure that they had on their own, their own sites and move those into the cloud. And they had solutions for virtualizing the servers, but they also wanted to be able to virtualize the networks. So you could take a network that you were running locally and just seamlessly move it over to the cloud, and it would run functionally just like it had run on your own site. And so this needed a kind of programmability to realize these virtual networks. Another killer app is traffic engineering. So again, motivated largely by these large cloud networks. Any of the current large cloud providers has a massive worldwide network that they build, maintain, and manage, and it's hugely expensive. And so they'd really like to use all of these expensive transoceanic links and expensive leased lines from telcos and ISPs and such. They'd like to use it as efficiently as possible. And so they'd like to be able to have algorithms and protocols that can optimally decide how to send the traffic through their wide area networks. And that's another form of kind of programming you could want to do that this vision of top-down programmable networks has enabled. There's also been a lot of work on network monitoring. So traditionally, it's kind of hard to figure out what a network is doing. But if you have the ability to write a program that maybe can collect some state and give you really fine-grained, detailed visibility into what's going on in a network, you can even look at delays and queues and loss. And so there's a whole class of programs that are implementing these network monitoring kinds of applications. And then maybe most exotic, there's a set of services and some people who have been working on what they call in-network computing. And this is really kind of rethinking the division of labor between the programs that run on the end hosts in applications and the programs that might run in the network. And so, this is a bit controversial, actually, but folks who are proponents kind of make the case that there are certain services that you might want a network to provide, like maybe caching some content, maybe giving you some protocols for coordination, things like consensus or distributed locking, failure detection. And so if you have the ability to program the network elements, you might be able to implement those in the network itself efficiently and just provide those as services for applications. Okay, so this is just a taste, and the talk is not going to be about applications, but just to give you a sense of kind of why you might want to program a network, you can have these in the back of your mind. So before I dive into kind of the design of languages, let me tell you a little bit more about kind of the architecture of these programmable networks. We're going to focus mostly on what's called the data plane, sometimes also called the forwarding plane. So this is the part of a network that actually moves data around. This, again, is just a cartoon, but if this is sort of a visual of a router, and inside the router there's some specialized hardware that can move bits around. And the details vary from device to device and vendor to vendor. But at a high level, what they mostly do is they take in packets, which are just bits. They somehow parse out some relevant information that's going to be useful for processing those packets. They extract things like headers and maybe some other information. And then that parsed packet gets sent through a pipeline where the data can be examined, manipulated, transformed. And usually that's done by sending it through a series of high-speed lookup tables that contain so-called entries, forwarding entries. So you can think of this as kind of a big conditional. The packet comes in, it gets parsed, it has some values, and then we look up these values in the table and then execute associated actions that then determine what happens next. And the actions can include forwarding the packet, dropping the packet, or maybe manipulating some of its values. And then finally, we send the packet out and rather deparse it and then send the packet out. Okay, so that's the sort of hardware view of the data plane. There's also this other piece of a network that's often called a control plane. And I'm not going to really talk too much about the control plane in this talk, but just to kind of give you a complete picture, this is also an important part of the story. This is where a lot of the logic that you actually write to customize a network and implement these services would live. And the control plane communicates with the data plane through an API that allows it to reconfigure the data plane's functionality, doing things like manipulating those entries in tables or querying for certain state, like statistics or counters. And so there's this other half of the picture that I mostly won't talk about today, but is an important part. Okay, so I want to move on now and talk about the design of new abstractions for these kinds of programmable networks. And I'm going to mostly focus on the data plane, and I want you to think about what kinds of abstractions you might like if you were trying to write a program that might do something special in one of these networks. Maybe it's a new kind of routing protocol. Maybe it's a new kind of way of forwarding packets to certain endpoints that want to receive it. Maybe it's a form of monitoring. Maybe it's security. So we'd like to be able to do this. And as a programming languages person, I'm kind of always looking to abstract. And so I kind of look at what the hardware elements have, these pipelines of forwarding tables that I showed you a couple slides ago. And that's ultimately sort of what the devices can do. That captures their expressiveness and their capabilities. But just as we don't program a server or an ordinary CPU by writing machine code, we tend to write Python code or something. I think it's interesting to consider if we could have different kinds of programming constructs for these network processors as well. And so there are many approaches you could take, but one that I think is pretty attractive is to have a higher level and functional abstraction that lets you think about programming the network as a whole in terms of simpler, compositional, and what you might call more declarative programming abstractions. And so in particular, I'm going to focus on a language where every program describes functions. These functions take in packets, and they spit out packets as outputs. And I'm going to be a little bit abstract for now, but note that these functions are really describing kind of end-to-end behavior. So I'm not talking about what happens on a particular router. I'm certainly not talking about what happens on a particular forwarding table. I'm really just talking about functions that I can kind of glue together to get what I want. Okay, and I'll take the next few minutes to kind of take us through a thought experiment of just kind of designing a little domain-specific functional language for this kind of data plane programming, just working by example with the kinds of things we might want to do. Okay, so we'll start by just thinking about a network that's kind of trivial. It has just one switch. And we're going to somehow write these functions that take in packets and produce packets. I should tell you first what a packet is. Eventually we'll generalize this, but for now, I want to think of a packet as just being a record. So it's a record that has some set of fields. Those fields would include things like standard headers, which have source addresses, destination addresses, various other kinds of information. I'm going to do one thing that's going to be important. I'm going to treat the location of the packet as just another kind of field in this record. So normal packets don't actually kind of carry the location along with them. But in this model, I'm just going to say, if this packet is parked at this particular switch, I'm going to call these elements switches instead of routers or other things. So at this switch, let's suppose its name is A, this packet would have the values you see here reflecting its location, including both the switch name and the port where it's currently parked waiting to be processed. Okay. And for people who have seen some of this work before, you might kind of be wondering, oh, is this the right type I want for this functional language? Do I really just want to have functions from packets to packets? Later on, we'll extend this so that we can keep track of a trace, what I'm going to call a history. So a trace that records kind of every step that the packet took as it went from element to element through the network. But for now, we'll just elide this detail and pretend that we're just writing these functions from packets to packets. Okay, so what's the most important thing you could want to do in a network? Well, you could want to forward the packet to some other location. And to do that, I'm going to have a construct I write it like assignment. So you can just read this as, set the port to 2. And if I evaluate this program on this input packet, shouldn't surprise you that what's going to happen is, well, I assign the port to 2, and operationally, the packet gets sort of moved from where it's currently sitting, port 1, over to port 2, and then it gets forwarded along its way. Okay, so that's our first thing. And a little note that although I'm using the notation of kind of imperative programming here, I've got an assignment of a particular field in the packet. This is still a pure function, right? There's no state here outside of what's in the packet. So I can run this program many times. The same thing's always going to happen. Packets that are located anywhere get forwarded out port 2. Okay, so what's the next thing we want to do in a network? Well, we probably care about forwarding packets not just across one element, but we'd like to be able to forward packets through the network, maybe on different paths. So for now, I'm going to give myself another kind of primitive that kind of captures a different kind of forwarding. So here, this A arrow B will stand for a little function that takes packets that are located at router A, switch A, and moves them over to switch B. And this kind of program, I should only write when there actually is a way to get from A to B, like there's a link between the two. But again, in my programming model, I can just say forward the packet from A to B. Okay. Next, I'm going to add conditionals. So conditionals are important because if you think about what a network does, it really takes any packet whatsoever. It classifies it, so it parses the header fields, does all these lookups and tables, and then it applies different programs to different kinds of packets. Packets that are supposed to go to Google get sent to Google. Packets that are being sent to Netflix get sent to Netflix, and so on. So we need some way to say, take in any packet whatsoever, inspect it, make some decision, and then apply different programs to different kinds of packets. So I'll use conditionals for that. And so I'm going to need some kind of predicates or some way to classify packets. For now, I'll just have these simple predicates that test if a particular field, say f, matches some value, say n. And then I'll have, as usual, a true branch and a false branch, here written p and q. And so this lets me now have programs that make decisions. Packets where f is n will go on the orange path indicated by p, and packets that don't have f equal to n will go on the green path indicated by q. Okay, next, we probably want to have some way to build bigger programs out of smaller ones. There's many ways you could do that, but one of the most natural is composition. So if I have two programs, here I've written it f and g, and f is maybe capturing some green path. Here it's just going across one link, but more generally it could take it could capture a bunch of processing going through a large region of the network. And then I have some other program, G, that captures some other processing. I can glue them together, and I get a program that does the end-to-end composition of the two. And then last, this is maybe a little bit weird because generally network data planes are not supposed to have loops. If your network has a loop, that's a bad thing because it means that packets could, in principle, cycle around forever and ever, consuming resources on all the elements in the network but getting nowhere. But at least from a sort of logical perspective, it can be convenient to say, I'm going to describe kind of how to do one step of processing, and I want you to do that processing until you can't anymore. Like, maybe I'll describe how to get on the next step towards some destination, and I want you just to do that until either you exit the network or reach the destination. So I'm going to put in loops, and I'll use just standard while notation. So while some condition holds, do f. And this will repeatedly do f. F could be some program that describes maybe all of these links, and we'll just iterate following links until we exit. Okay, so hopefully that was a little bit fun, just kind of doing some language design. What have we actually done? Well, I didn't show you all these constructs, but with a couple of other additions, which hopefully are natural and obvious, we've really designed kind of two little languages. So on the left, you can imagine that we have a language of Boolean predicates. We use those both in the conditionals and in the loops just to capture facts about packets. So these things describe sets of packets that satisfy the predicate. And then on the right, we have these little functional programs I didn't show you every single construct, but we have an identity program. We have a program that drops everything. We have the program that assigns any field, including the port, to a certain value. We have composition, conditionals, loops, and then this special link forwarding construct that moves a packet from A to B. OK, so a little language, and you can already write lots of interesting programs that take different kinds of packets and move them through the network. OK, there's one little problem, which is, as written, this language is a little bit impoverished. So for every packet, it will either drop it. If we eventually execute this drop primitive, then the packet just stops, and the set of packets produced in the output type is empty. Or we keep forwarding it. We never take a packet and produce two outputs. And there are certainly cases in a network when you want to do that. If you're doing any kind of multicast or broadcast, you may want to be able to take an input packet and then produce several output packets. And this language right now can't express that. So what could we do? Well, we could just keep following our noses and add some new primitive, maybe like flood. And what flood would do is it would take any packet coming in and send a copy of that packet out every single port that's local to the current switch that we're on. You could do this. In fact, some of the early languages that I designed for network data link programming had exactly this primitive. There are some kind of weird puzzles that make you scratch your head, like if I compose flood with itself, do I produce like more packets? Do I get like somehow the square of the number of ports or something? So it's a little bit maybe of an odd primitive. I'm going to take a different approach, which will, and this is kind of something that, by the way, programming language designers often do this. When you're designing a language from scratch, usually start by having some domain that functions on packets. You have some idea for like what these programs should do, and then you start sort of adding primitives. And then you kind of check, do these things make sense? Do I have natural operations like composition, identity, and so on? And then sometimes you get to a place where you're like, wait, something's a little broken, and then you go back and refine. So I'm kind of going through that exercise of iteratively designing a language by considering this operator. And what I'm going to do is, rather than just throwing in flood as a primitive, I'm going to see if I could maybe generalize the primitives I have a little bit, and then just derive flood from some slightly more powerful primitives. And if you think about it, the reason that my language doesn't allow me to ever produce two outputs is that, well, all of my operations are really deterministic, right? I either, like in a conditional, I either do P or Q. I never do both. So, and same for a loop. Like for a loop, I go around the loop some number of times and then I stop. So I'm going to do a little trick and replace the conditionals with an operation that I'll write plus. And you can think of plus as being either non-determinism, or I like to think of it as union, sort of do both P and Q. And likewise, I'm going to take the loop and replace it with an iteration operation. So if you've seen regular expressions before, this P star is exactly like that. It says do P 0 or more times. And doing P 0 times is like identity, and doing it more times is like composing P with itself. OK, so this is kind of fun. And if I do this, there's a couple of standard encodings that let me get back the conditional and loop. So for conditionals, that's really just a special case of this plus, where the programs that I'm plussing, on the left, I have A, the predicate that I was had as the guard of my loop. I'm going to treat A as a filter. So I'm going to just sort of run the predicate and think of this as a program that allows any packets that satisfy A to go through and drops any packets that don't satisfy A. And I'll compose that with P. And then I'll plus that with the negation of A, so not A. And sorry, that should be a Q, not a P. OK, so I can derive the conditional just from this non-deterministic union. And there's a similar encoding for while loops. I basically guard the body of the loop by A, iterate that, and then exit the loop when A no longer holds. And my flood primitive, now I can get it just by using this plus operation and saying, well, so this would be specific to a certain switch. There's a little bit of bookkeeping that I'm glossing over here. But essentially, I can just take a union of set the port to 1, set the port to 2, set the port to 3, all the way up to set the port to n, where n is the biggest port on the device that I have. So this will create n copies of the input packet and then move them to the output port for every single output port. Okay, so that's my sort of revised language. I'm going to clean this thing up oh, question? Arbitrary but finite, yeah. Yeah, so in a denotational semantics, if the while loop didn't terminate, it would not produce any outputs. So that distinction won't matter in a denotational model of these. We'll get to that a little bit later. Okay, so I'm going to do a little bit more of tidying here. So this is another thing that programming language people often do is, although we're interested in writing, languages that have all kinds of nice surface syntax and are convenient to use, when we're doing design and trying to kind of model things mathematically and build tools, it's really nice to have little languages. So we often try to kind of distill things down to their essence. So the next thing I'm going to do is I'm going to just change the syntax of a couple of my operators. So I have this ID and drop programs, and I have Boolean conjunction and disjunction, which I haven't used, but hopefully you know what those mean. And I'm going to just change the notation. So I'm going to write ID as true and drop as false. That's consistent with what I was showing you before, where I was using predicates implicitly as filters. So if I use true as a filter, it just passes through every packet, because every packet satisfies true. If I use false, no packet satisfy it, so I get no outputs. And I'm just going to choose to write conjunction as semicolon and disjunction as plus. And why am I doing this? Well, just to tip my hand, I'm going to eventually smash these two things together, so I have just a single language. So I'm going to actually just give myself an arbitrary semicolon and plus that works either with predicates or with programs. And it will so happen that their semantics agree. There's one other little thing I'm going to do. So I had invented this primitive for moving packets between switches. And I already have a couple of primitives that kind of do some of that. So if you think about how you'd implement this A arrow B, well, I'd need to test, is the packet at A? And then I would set the packet as being at B. And I have a test f equals n. And if I choose f to be the current switch, and I can likewise set the current switch to be B, it seems like I could derive that one too. And there's this one other thing that this arrow primitive was doing, which I hadn't really explained, which is I want to think of the language as, sometimes I want to think of the language as giving me not just functions on packets, but actually keeping track of the traces or the paths that the packets took through the network. And so I'm going to give myself a new primitive. I'll call it dupe. And the name dupe is probably a little bit mysterious. It'll become clear in a little bit. But for now, think of dupe as just sort of delimiting when I go from one device to the next. And this A arrow B thing, I'll think of as being exactly what I said a couple seconds ago. Just test if you're at A. If you are, then do dupe, because you've reached the end of A. And then assign the switch to B. So this captures this kind of forwarding between switches while recording that we took another step on our path through the network. Okay. So the final take, and this is the netcat language, is obtained by, now that I've done this kind of massaging and simplifying, I'm going to smash these two languages together. And the whole reason that I made the Boolean operators look like plus and semicolon was to be able to do that. And I get this language. So this is a little language that captures everything we've seen. And if you just kind of zoom out, like, why is it the way it is? Well, it's one of these minimal core languages, but it has logical predicates that let you classify packets. It has the regular operators, so concatenation, union, and star, which lets you build up these interesting paths. And then it's got a few primitives, assignment and tests and dupe, that let you capture some elements of how you forward packets through a network. Okay, so that's our little exercise in language design. And I'll just say one comment, which is, of course, this language is simple, and there's lots of things it doesn't do, right? It doesn't model situations where the switches have state, and that state could be manipulated by packets. It doesn't model the control plane, as we've said. So there's a lot of stuff it leaves out. But we've done some work that actually generalizes the language in that way. But it's also useful to have this language just as an abstraction of just the kind of basic functional forwarding that networks do. OK, so the next thing I want to do is tell you a little bit about some of the work we've done compiling this language. This is, why do we care about compilation? Well, if you have programs, you want to be able to run them. And it turns out that working out the details of how this compiler works, both, when we were doing it, it kind of, taught us some things about the language and its underlying structure, and it also helped us gain confidence that this design was useful. And as motivation, I want to use a paper written by some of my friends at Princeton. So this is an old paper from SIGCOMM 14 called SDX. And they were interested in building programmable networks for internet exchange points. So these are the sort of giant routers where multiple entities, including telcos and ISPs and content providers, come together and peer with each other. And there are companies that basically run these exchange points, allow people to come hook up, and then the vision here was to allow the different participants in this exchange to write some custom code to kind of capture their peering policies, and to do this using the same abstractions that I've been showing you. So this Princeton group had a language that was very, very similar to Netcat. And they were interested in one aspect of Netcat that I haven't emphasized, which is the language is kind of compositional at its core. So we kind of threw in composition just because it seemed like, why not? But from a more practical perspective, if you have the ability to compose whole applications, whole data plane applications, that's really powerful, right? That really shows how having this abstraction where I'm just thinking about there being functions, and then of course I can compose them together, is really enabling. And if I was way down at the level of the hardware and programming the tables, it wouldn't be obvious how I could compose things. So the Princeton folks were interested in things like, maybe a particular participant in this exchange wants to have some access control function that they write, and then they have their routing function that describes how their traffic gets sent to other participants in the exchange. And eventually, of course, this gets compiled down into the tables of that giant router that is the exchange. OK, so I don't want to spend too much time talking about the details of the system. I want to zoom in on one of the graphs in their paper. And these really are my friends, so this is not meant to beat them up, but just to motivate the work that we did. So they built this compiler for their language. And the compiler was taking all the programs that came from the participants. They got combined together with something like our plus operator, and then ultimately compiled to these tables that run on the routers. And of course, you would like this compiler to be fast, because you'd like to be able to sort of update the forwarding state as quickly as possible. And this is the graph from the SIGCOMM paper that shows, on the x-axis, the number of different IP prefixes that were referenced in their policies, and then the time in seconds that it took to compile it. And the curve is going up and to the right, and pretty sharply. And so the thing to note is, in their experiments, for 300 participants, they kind of did some synthetic benchmarking. The compiler was taking about 10 minutes to produce the forwarding state. Maybe 10 minutes is OK, but to me it seems like a long time. And if you kind of look at what real exchange points have, that's from Wikipedia circa 2015, real exchange points have at least double, if not more, that number of participants. So it'd be really nice if we could have this vision of having kind of declarative programmable exchange points where the policies are written in a modular way, but have a fast compiler that could produce the forwarding state, so we could allow the participants to update themselves and make this work. And I'd say one more thing. There's a little footnote here. This graph was actually obtained after trying to do some optimization of the compiler. And it turns out that some of the optimizations themselves were unsound. So they were trying to sort of speed up certain aspects of compilation, but there were some mistakes. So these graphs are even suspect because the output of the compiler was wrong. OK, so we did some work in ICFP 2015 where we said, OK, we've got this netcat language. We've got these programmable switches. Could we build a fast compiler that would allow us to sort of drop in our compiler for the SDX compiler and maybe do it in seconds instead of 10 minutes? And could we also think about compiling some of the other rich kinds of abstractions that netcat allows you to express beyond just a program that runs on one device? So in particular, we wanted to be able to somehow handle these global programs where you're not programming one device but are just describing the end-to-end behavior. And we also wanted to handle programs written for virtual networks, which I've mentioned as a motivation but haven't shown you the details, but we'll see that in a little bit. And we were able to do that. So we had to do some work designing new data structures and designing new compilation algorithms. We were able to come up with this whole pipeline, and the pieces really fit together, where there's first a local compiler that can take a program written for one switch, so a program that never uses that A arrow B or that dupe operation, and we can compile that to a set of tables for one switch. Then we have a global compiler that can take a program that does use those features and then produces a set of local programs, one for each switch, that implement the same behavior. And then on top of that, we showed how to implement network virtualization as well. So I'll take you through these pieces one by one. We'll work bottom up. So we'll start with the local compiler. This thing takes, again, a program that doesn't ever forward packets to another switch. So it just describes a function that's going to run on one single device. And it outputs, here it says a collection of float tables. You can think of it just as like one table for that switch. And of course, the main challenge is we'd like this to be fast. So to motivate our approach, let me tell you about how SDX and other similar compilers were done at the time. So the idea was roughly, if we've got a programming model that has composition, maybe it has sequential composition, maybe it has union, well, if I've got a program that can be described as do routing and here monitoring, well, maybe I just recursively compile these things to tables, and then I have to figure out how to do the corresponding operation on the tables to merge them together. So in the case of plus, plus implements some kind of set theoretic union, like you can think of like all the packets that would be produced by evaluating either table should be in the output. And union's kind of particularly tricky because the only way I know how to do this is basically to take some kind of quadratic, consider every possible pair of rules in the two tables and how they might overlap or not overlap, and then produce the union. So this is not very fast. And shouldn't really surprise us. I mean, why are we compiling in terms of tables? Like, tables are the ultimate output. But if I was a compiler designer and thinking about maybe an intermediate representation in algorithms, I probably wouldn't start from these hardware tables. So we tried a different approach. We kind of looked at what was expensive in building these compilers. And it's true that these netcat programs, they have some primitives that correspond to forwarding and manipulating packets. But really, for real programs, the thing that really dominates are the predicates and the classifiers. And that corresponds to sort of the structure and size of the tables. And so if you look around in the literature, there's some really nice data structures that people have invented for dealing with Boolean classifiers, Boolean predicates. And there's a whole bunch of them. Broadly, they're called decision diagrams, binary decision diagrams, and many variants. So we thought, let's try and use BDDs and a slight variant of them to build our compiler. So now, instead of compiling via tables, we'll have an algorithm that can recursively compile the pieces of a program to one of these decision diagrams. And then, well, it turns out we didn't have to even think that hard. Most of the algorithms that we'd want to do, like taking the union of two such things, there are existing algorithms in the literature on BDDs. And these algorithms are often, there are best case algorithms that are known, and even efficient implementations that we can either steal their strategies or even use highly tuned up implementations. And so, okay, so we can then do the operation on these diagrams. Now we have the result. And now, of course, there's a last step, which is ultimately we do want a table. So at the very end, we've got the diagram for the whole program, and then we have a procedure that can basically sweep over that diagram and produce the table. Okay, so just a little data structure and algorithmic trick that is asymptotically more efficient and also works really well in practice. So how well? So here's a plot from our paper. We took the same inputs. We actually just reran the SDX experiments. This is, by the way, how we discovered that their compiler had a bug, because we had some validation, and we were doing fuzz testing and generating lots of random programs, and we initially had lots of bugs in our compiler as we were building it, and then we eventually got those bugs out, and we were like, wait, why do we have a different answer here? And it turned out their compiler had a bug. And the dashed lines are the SDX plots. You see those are going up into the 10 minutes territory, and our compilers are these are for different numbers of participants in the exchange, but our compiler finishes all of them even out to the 300 and beyond in just a couple of seconds. Okay, so that's the local compiler. Let me level up now and talk about the global compiler. So previously, we said the input to the local compiler is a special case of a program where we never forward the packet to a different device. So now we're going to take an arbitrary program where we do possibly do that. And the output of this compiler is going to be a set of local programs where we've got one for every switch. Okay, and the challenge is we need to find a way to produce these local programs that can make local decisions about how to forward packets while still being consistent with this global program. I'll show you what that means in just a sec. So here's maybe a motivating example to illustrate. So suppose I have this kind of trivial but barbell topology. So I've got just two devices, and I'm going to think of traffic going left to right. And what I want to do is implement the two red arrows that you see. Think of these as tunnels. So I want to take packets that come in on port 1 on switch A. I want to move those through the network and then spit them out port 5 on switch B, and the same for the lower path. So if I don't give myself the full power of Netcat, and I just think about, let me write programs for each of the switches A and B that do this, well, for switch A, it's maybe easy, because A actually forwards everything out port 3. I have a Netcat program that does that. But now on B, I'm kind of stuck, right? Because I receive all these packets from switch A, but I don't have any way to decide which ones came from port 1 and which ones came from port 2. So I really don't know, where to forward the packets on port B. Okay, so what would I do? Well, I need some way to remember on port A and actually store that thing that I remembered in the packet so that on switch B I can then make the right decision. And if I don't make other assumptions, maybe I know that only certain source addresses live off these ports, then I could use that. But if I don't have that, if I really want these things to be tunnels, then I'm going to have to do some kind of tagging. And for now, I'm just going to pretend I have some field called tag, and I can assign that field on switch A. So I can now, rather than just forwarding out everything out port 3, I'm going to condition on, am I coming in on port 1 or port 2? I'll write the tag variable to remember where I came in. And now on switch B, I can test that tag value and forward appropriately. Okay, so this gives you a sense of, some of the complications if you take what started out as a simple description of global behavior and I want to realize it locally. I need to, invent these tags, come up with values, coordinate them across multiple devices. So this is not so easy. So in Netcat, I would not write this program, right? I don't want to think about tags. I would just write this program, right? I would say, okay, I've got these two tunnels. The first tunnel starts at port 1, and then I go from A to B, and then I go out port 5. And the second tunnel starts at port 2 and go from A to B and go out port 6. So this is a perfectly legitimate Netcat program. It implements exactly what I want. So it's simple, but now, hopefully it's clear, if I'm going to compile this thing to local programs, I somehow need to compile this into something like the program with tags that I showed you. So that's sort of the crux of what the global compiler is going to have to do. Okay, so what are the main challenges? Well, we've already seen this, right? So if I've got these possibly end-to-end paths described by the regular operators, I've got to somehow come up with some scheme for how I can keep track of the state that lets me remember where the packet is and what still has to happen. So there's some tagging. Once I show you how we've done this, it'll be kind of clear, but I'll just quickly say there's some sort of obvious approaches. Like you could imagine, like maybe I keep some kind of program counter, and the program counter kind of advances as I go through the global program, and then I maintain that on the switch. There's some naive ways of doing this where if you did this, you'd end up with extra packets. You'd sort of duplicate the packets too often. And in particular, like if I use the union operation, Netcat's union operation really stands for a set theoretic union. It says, the outputs, the final packets that you get, the final histories that you get at the end, should be the set of things you got. And so if I were to duplicate the packet at A, but then eventually those packets on B landed in the same place, then I should have not duplicated them. So there's a little bit of complexity in basically deterministically deciding to only duplicate a packet when you must. Okay, so our solution is to implement a scheme that basically keeps track of a kind of program counter. And we take advantage of the fact that Netcat is ultimately based on these regular operators. So we can take our global program, we can compile it into a kind of automaton. It's similar to the kinds of automata you learned about in undergrad theory of computation. It's got a few extra details because it's Netcat, but essentially it's very similar. And then the states of that automaton become the values of the program counter. So we start out in the initial state, and then as we take transitions, the state advances. And the state always tells us, locally what should happen at the switch that we're presently at. In order to handle this problem with duplicating packets too early, it turns out that's exactly just making sure the automaton is deterministic. So if we have a deterministic automaton, then we will copy exactly when it's appropriate to copy the packet and not when it's not. And we can even do some optimizations, like we could try to minimize or at least shrink the automaton, and that would reduce the number of states, which would reduce the space of tags that we need to keep track of in our implementation. Okay, so I'm not going to show you a formal definition, but this is the sketch of how our compiler works. Let me tell you a little bit about these automata. So they're very similar to the kinds of automata you've seen on just ordinary strings, but again, it's Netcat, so there's a couple of differences. The main thing I want to show you is that the transition function has this kind of funny type, which I've written out here. So the transition function, use delta as is conventional, takes the current state we're in, it takes the current packet, and then it produces a set of next states and next packets. And hopefully it's clear, like the packets are kind of like the characters in a regular automaton. So the packet kind of captures the current state of the thing we're looking at. But because Netcat programs can modify values in the packet, we have to also produce this output packet. And so the sort of continuations, if you like, of taking a transition include both the next state to go to and the new value of the packet. So that's just a little bit about the automata. From a practical perspective, there's a couple of challenges in realizing this. One, which maybe is kind of obvious, is that, well, the alphabet size here is kind of packets squared, and there are a lot of packets. So, so naively, realizing these as DFAs would blow up. But it turns out that we can actually represent these automata symbolically using the same kinds of data structures I showed you for the local compiler. I'm going to defer showing you this in detail for a couple of slides, but for now, that's the intuition for how these automata work. And we can also build these automata using some fancy techniques from formal language theory. I'll also show you this a little bit later, but there's this notion of the derivative, which is an operator you can apply both to kind of programs or regular expressions, and it gives you the transition structure of an automaton. So that's how we build these Netcat automata. Okay, so that's a little bit about the global compiler. Let me now tell you about the virtual compiler. And so here, the idea is that we want to write programs that are somehow operating in some logically separate space of packets and switches and such, and then we want to realize it on a physical network. That may be a bit mysterious, so let's go back to our example and I'll show you what I mean. So here was our global program that I said was simple and elegant, just what I want to write. But I can make it even simpler and more elegant. So suppose I abstract this whole network. Well, in this case, it's just two switches, but suppose I abstract this network so that instead of having two switches with a link between them, I just have one switch. And I think of this switch as being a virtual switch, so it's kind of, the whole network is one big switch. And it still has ports. The ports correspond to kind of the outward-facing ports of the real network. So in particular, ports 1 and 2, correspond to the ports 1 and 2 on A, and I've named things consistently. Ports 5 and 6 correspond to ports 5 and 6 on B, but there's no port 3 and 4. That's really hidden in the implementation of this virtual switch. Okay, so if I can do this, and the dashed lines here are meant to kind of remind you of the connection between this virtual switch and its locations and where they correspond to in the physical network. So if I had this virtual switch, I could dispense with having to forward entirely. I could just have a local program that says, yeah, port 1 is wired up to port 5 and port 2 is wired up to port 6. So that would be even simpler. But now I have to somehow implement this. And again, like this is a cartoon example, but this is really this was sort of one of the killer apps for programmable networks, was the ability to define these virtual networks. And in practice, they include more than just one switch. You can define whole virtual topologies, and then essentially emulate those on a physical network. And you can do it not just once, you can do it with many virtual networks that get multiplexed together onto the same physical network. So our compiler can do all of that. I'm just going to show you how it works with kind of this toy example, but that's the vision for where we're going. So the key thing that the virtual compiler needs to do is there's certain locations in the virtual network that correspond to locations in the physical network. And I've drawn those with dashed lines. At a minimum, this will include, somehow the ingress and egress of the network need to really exist. So there will be some sort of initial and final locations that are related to each other. And so when I have a packet that starts out, it starts out in this relationship. I can think of the packet as being, consistent with where it's supposed to be. But now, when I run my virtual program, maybe I forward the packet, now I've got, my physical packet, nothing's happened, but my virtual packet has moved somewhere else. So I need some way to sort of match the moves that were made in the virtual network and do the same thing in the physical network. And the moves that were made in the program, those are easy. I can just run the same program downstairs. But in this case, forwarding just across the switch now needs to take a whole path through the network. So I need to find some way where I can basically take every packet that started out in some related location, virtual and physical, took a step, became unrelated, and to then restore that relation. So in this case, I need to find some path through the physical network that will restore this property of being in related locations. And this is a really cute thing that my student Stefan Smolke came up with. You can formulate this kind of execution of a virtual network. The crux of it you can view as kind of a two-player game. So the one player is the person who writes the code for the virtual network. And they get to play a move by, they start in one of these related locations, and then they can take any move whatsoever in the virtual network, and they're trying to kind of break the property of being related. And then the other player, once the virtual player moves, the other player is the physical network, and it has to match the moves. So it has to find a way to come up with a corresponding move in its topology that will restore this property of being related. So our virtual compiler literally formulates this kind of game theoretic view, and then finds a winning strategy. So using properties of the topologies, it finds a way for the physical network to always match the moves of the virtual network. And in slightly less mystical terms, what that means is every sort of every one hop in the virtual network gets realized with a path in the physical network. And in general, there's choices you can make. So our compiler actually allows you to sort of optimize for different choices. Like you can balance the physical paths out, or you can make them fault tolerant, or lots of other choices. But the crux of it is winning this kind of game. OK, so that's the virtual compiler. Let me just show you this thing in action. So here's a picture of the virtual compiler as you might use it. So here's a less trivial tree topology. Here's a virtual network. I've drawn it the other way around this time. And you can imagine that if I was a tenant of a cloud network, I might want to sort of have machines that are located at the bottom of the tree that I want to program with one switch. And I want to write policies like you see in the yellow box. And this is a slightly cleaned up output of our compiler, but the Netcat compiler really produces this kind of output. Given this particular program and this relationship between virtual and physical, it will produce tables that look like this. And in this case, what I'm showing you is, I believe, on switch 1, which is the top of the tree, I'm showing you the program for this scenario. And here the thing to notice is we're matching on the addresses of the servers and then forwarding them out on the path towards that server. So that's what the virtual policy did, and we're realizing that in the physical network. So to take maybe the first one, a packet that comes in on port 2 that's going to host 6, we're going to output out port 5, which is the next step on the path towards that host. OK, so under the hood, what's going on is we ran the virtual compiler. This produced a global program with these forwarding paths. Then we ran the local compiler on the outputs of the global, which gave us the tables. And just to show you, this is a plot of the automaton for the global program we got for that particular virtual network. It's a little bit hairy, but essentially it captures the network-wide behavior needed to realize all those paths. OK, so that's enough about the compiler. Let's see, I have about 20 minutes left, I think. Oh, yeah, question. Yeah, so I'll say two things. So one, I glossed over this, but one way you can run the virtual compiler is to ask it to find paths in the physical network that will never depend on the virtual program. Let me say it a different way. Sometimes you can use, if you know the virtual program, you may be able to be smarter about which physical paths you used. But that makes your final produced physical program more brittle, because now if you change the virtual program, maybe you need to recompute the paths. So we have one way of running the virtual compiler where you basically choose not to look at the virtual program, and you only lay down these paths. They basically become tunnels, and then you only have to change sort of one place to update. If the virtual program changes, you only have to make local changes. So, yeah. The other thing I'll say is I have also glossed over anything having to do with like incremental recompilation. And in practice, of course, that's pretty important. That's sort of arguably the whole reason for the distinction between the data plane and the control plane is that, not the whole reason, but one of the ideas is that the control plane can sort of make incremental changes and then transmit those to the data plane, and it's a pretty efficient thing to do. Our compiler was not incremental, but our Princeton friends did look at incremental approaches. So, it more or less goes how you'd expect, but you need some slightly generalized algorithms to say, if I have a series of programs and I'm making changes, maybe I'm tweaking the forwarding for individual hosts, can I come up with small edits to make to the table so I don't have to redo everything? And you can. Okay, so any other questions? All right, so I want to now, all of that was sort of a warm-up to give you just a sense of, what's possible if you take this approach of designing a higher-level language, how might you implement it, and a little bit about the structure. I now want to do a little bit of a deeper dive, so maybe this is for the programming languages and formal methods people in the audience. If you're not a programming languages and formal methods person, don't be too afraid by the Greek letters you're about to see. It's just, PL people just have to do it, so it's not, there's nothing too mysterious or complicated here. So another reason to have this kind of abstraction for networks is that we can reason about it. And this has become sort of a whole area. Both large companies now have teams that are doing formal verification of networks, often based on these kinds of models, and as well as there's government programs and startups and so on. So what we'd like to do is first to have an understanding of the underlying mathematical or semantic structure of these programs. And in the case of Netcat, we can do that not just one way, but in several ways. So until now, we've really been thinking about this functional model. Programs are functions. And the fancy way of saying that is we have a denotational semantics for Netcat. We can take every program and figure out what function it denotes. But there's other approaches. There's so-called axiomatic semantics, where we think about programs and what kinds of logical formulas or predicates they might satisfy. And there's also operational semantics, where we think about programs as really describing some kind of machines that do stuff. We've already seen a taste of that, because I've shown you that Netcat programs can be thought of as automata. And more generally, these three different ways of describing language semantics, well, Netcat has all of them. And we can even relate them to each other. So, for example, in going from the functional model to the automata model, you can actually transform Netcat automata into programs and vice versa, just like you can take regular expressions and convert them into automata and vice versa. So that's sometimes called Kleene theorem. In the same vein, Netcat has a kind of axiomatic, or if you like, logical semantics. I'll show you that in just a minute. And that thing is both sound and complete. So the axiomatic proof system that we have is sound. Everything you can prove is true relative to the denotational semantics. And it's complete. So anything you could hope to prove, you can prove. And then we've also done some work doing something called proof-carrying code, where we think about taking the proofs that we get from Netcat programs and actually shipping that around in a distributed system, which is kind of fun. So that's maybe a way to connect the set of axiomatic to something more operational. Okay, so I just want to kind of take you through a little bit about, a little bit showing you what this looks like. Let me, I'm going to skip over this because I'm a little short on time. Remembering the structure of our domain-specific language, I kind of said, well, really what this thing is about is we have a language of predicates, we have a language of regular expressions, we have some primitives, and we glue these things together. It turns out that if you combine a language of predicates with regular expressions, we were not the first to do that. There's a system called CAT, which is shorthand for Kleene algebra with tests, which is exactly that combination. So what Netcat is really, it's this CAT system, which my colleague and collaborator Dexter Kozin, he invented in the 90s, sort of instantiated in the networking domain, and then with a few extra primitives. So why is this interesting? Well, Dexter's a theoretician, but the whole reason he has for studying CAT is he's interested in coming up with nice proof systems for reasoning about program equivalence. So if we have two programs, P and Q, he wants to have a proof system where we can show that P equals Q. What does that look like? It's a little bit intimidating, but I just want to show you it's a relatively simple system. This is the whole thing. So these are all of the axioms that you have for, well, cat is the left-hand side in the upper right, and then netcat is what you get if you throw in the lower right as well. So each of these you can think of as an axiom. And what it tells you is, if you have a program that matches the form on the left, that thing is equal to the form on the right. I'm not going to read them because there's dozens of them, but I'll just quickly say they capture very natural, kind of obvious things that you'd expect. For example, the union operation is commutative and it's associative, and it distributes over sequential composition in the obvious way. So many of these are kind of obvious. Boolean algebra axioms you all know from some logic class. And then the packet axioms, these are the only things we really had to think hard about. And we didn't think that hard because it's kind of a simple model. But essentially, it just captures how these tests and modifications interact with each other. Okay, so again, I'm not going to teach you the details because the details you can read better for yourself in a paper. But the point is, we have a proof system that lets us reason about equivalence. Why might you want to do this? Well, a standard answer is, this could really be how you sort of do simple forms of verification. To motivate that, let me just consider a toy topology like you see here. So I've got a machine on the left talking to a server on the right. And if I'm the network owner, maybe I want to block certain traffic, like SSH traffic or something. And in this network, I have sort of two places I could do the filtering. So I could block the SSH traffic on switch A, or I could do it on switch B, or I could do it on both. And there might well be good reasons to do it on A versus B. But from a functionality point of view, viewed through the lens of Netcat, these things are equivalent. Right? So if I take this program where I do the filtering and dropping, I'm going to just call that firewall. So I drop the packets at switch A, and then I just let switch B pass through the packets however it wants to. That's actually equal, again, in the Netcat model, to doing the blocking at switch B and letting A pass things through. And where's the proof? What does the proof look like? Here's the proof. It's the whole thing. So it's a little bit involved, because you have in this proof system, you have to kind of justify every single step. But essentially, this is the end-to-end proof. Up on the top, I have the version where we do the filtering at switch A, and down at the bottom, where we do it at switch B. Okay, so these axioms can establish these kinds of, if you like, some kind of optimization or some kind of program equivalence. Okay, so that's kind of cool. What's maybe more cool is this theorem that I flashed up before. Generally, if you have a language and you have some program logic or some kind of proof system, you probably want it to be sound, because if the proof system or logic is not sound, then it's not useful. But it's pretty rare to have a system that's complete. And Netcat's axiomatic proof system is complete. Why is that? Well, Netcat's a simple language, and ultimately it can be described in terms of finite structures like automata. So maybe it's not too surprising, but it's still kind of remarkable that it works. So I want to give you just a quick taste of kind of how this completeness result goes. The next few slides will be the heaviest part of the talk, and I'll just say if you're kind of falling asleep or can't follow the details, the gist of it is we can basically take Netcat programs, normalize them into a particular form, and then they become just like ordinary regular expressions. And Dexter proved a result 20 years ago, 30 years ago, that the Kleene algebra axioms are themselves complete for any regular model. So we basically reduce it to a theorem that Dexter already proved. Okay, so with that roadmap, here's how it works. So the first thing I'm going to do is I'm going to take Netcat, which is already pretty simple, and make it even simpler. So I'm going to take all of the tests that I have, these f equals n predicates, and I'm going to force you to do what are called complete tests. So every test that you have in your program will have to test every single field. So you can't just say, is the IP address 17? You have to say, am I at switch A? Is the port 7? Is the IP address 17? Is the source address 15? You have to write out a full test for everything. And the same for assignments. Okay, so this is like pretty heavy-handed. You wouldn't want to do this in programs, but for a proof, it'll work. Once we do that, we can simplify the language to look like this. So we kind of get rid of some of the apparent complexity. We have these complete tests, complete predicates, if you like, alpha. We have complete assignments beta. We have the regular operators and dupe. So that's it. And just for examples, I'm just going to work with just two fields so it doesn't blow up. You can do this with arbitrary number of fields. And you can pretty easily prove that if you start with a Netcat program in the full language, then there's an equivalent program, and you can prove that it's equivalent, that is in this reduced form. So we can just work with reduced terms. Okay, so the next thing that would be tempting to do is, okay, we have these reduced terms, and I can think of these really as being just a regular language over a weird character set with alphas, betas, and dupes. So what if I do that? Well, I can take the totally standard regular interpretation. Here it is. Again, if it's too formal, this is exactly what you had in theory of computation. But unfortunately, this fails to have a property that would be nice. So if we have two programs that are equivalent according to our functional model, so they describe the same functions, it may not be the case that this regular interpretation of the reduced programs will be equal. And here's a little example that shows why. So here I'm writing them as, these are complete tests over my two fields that I'm considering, switch and port. And here I've written, so the first program is switch equals 1, port equals 1, switch equals 1, port equals 2. And I've underlined the complete tests, so think of these as like individual characters. And basically, this is a contradiction, right? I can never have a packet that's at switch 1 and simultaneously at port 1 and 2. It's either at 1 or at 2 or neither. So this is equivalent to false. And this program here is also equivalent to false. In this case, the contradiction comes from the switch as opposed to the port. So I can have programs. This is a reduced program. But if I interpret them just in the usual way, as strings, they're different. Right? These are not the same strings. OK, so I have to do a little bit more work. And fortunately, again, most of the interesting theorems in this work come from Dexter. Fortunately, I can. There's a different way of doing a kind of formal language interpretation of programs like this. They're called guarded strings. And essentially, what I'm going to do is I'm going to impose a little bit more structure. So I'm going to insist that my strings have a particular form. They basically alternate between complete tests, complete assignments, and dupe in a certain way. So that's it'll start with a complete test. It'll have a sequence of complete assignments separated by dupes, and then a final complete assignment. And you can put programs into this form. You can define a semantics where you take reduced terms and build this model. There's a little bit of details which I'm a little short on time, so I'll gloss over. But the intuition is now, if you like, the strings in this language exactly correspond to the trajectories that packets take going through the network. If you like, the initial test is sort of the test describes the input packet, and then all of the subsequent modifications, complete assignments rather, correspond to the intermediate packets that existed at some interior node. And the dupes tell us where we kind of went from one hop to the next. So you can build this slightly refined model. And now that theorem that I said didn't hold does hold. So two programs will be equal as functions if and only if this language interpretation is equal. And there's another lemma, which I'm not going to show you how it works, but there is a kind of normal form. You can basically do some further simplification. I'll write it with a hat. So for every program P, there's a normal form program P hat that I can prove they're equal, and where this language interpretation is, in fact, a regular language. So I could use the previous interpretation to get the same answer. Yeah. There is a kind of blow up here. I don't know the exact complexity offhand. But I think your intuition, which I think is correct, is when we build this normalized form, what we're doing is we're eliminating these contradictions by kind of multiplying things out. So there will be a kind of blow up. OK, so now I can show you kind of the skeleton of this completeness proof. So we're going to start by assuming we have two programs, P and Q, that are functionally equal. Now we're going to reduce and normalize them. So that gives us P hat and Q hat. There may be a blow up. I'm not going to worry about complexity. And I can prove these things are equal by the lemmas I have. And then by soundness, because the axioms are all sound, I know that P hat and Q hat are equal as functions. And now, by the theorem I showed you for this guarded language model, G of P hat equals G of Q hat. So this viewed as these kind of weird kind of strings, these sets of strings are also equal. And now, because over these reduced normalized programs, G is a regular language, there's an existing theorem from Dexter's which says that Kleene algebra is itself complete over any of these regular languages. So we can appeal to that theorem to get a proof that p hat equals q hat. And then by transitivity, we're done. OK, so that's just a little bit about the foundations. I'm going to have to skip over the next part because I have gone slower than I thought. If folks are interested throughout the day, I'm happy to tell you this is some recent work that we just published at PLDI, where we basically use some of the same. I'll just show you the upshot. Actually, this is the one I'll show you. So we use some of the same ideas, but generalized a bit from our compiler to build a fast verifier. So we basically built a verification engine that doesn't actually use these axioms. It just converts programs into automata and then checks if those automata are equal. And many of the kinds of verification questions you would like to do in a network, like testing if there's connectivity or if there's isolation, can be reduced to program equivalence. And the punchline is we can make this thing fast. So by picking the right data structures and some of the right encodings, we can make this fast. So the plots here are, this is for a synthetic benchmark where we used a bunch of real-world topologies. We generated a bunch of synthetic routing schemes over those topologies. And then we checked some properties. I believe this is checking connectivity between all of the exterior locations. And we compared our implementation based on Netcat to a state-of-the-art implementation called AP-Keep from some researchers, I believe at Tsinghua, building on some work out of UT Austin on something called AP that uses a SAT solver and a bunch of optimizations. And we were very happy that our automata-based tool that doesn't use a SAT solver and doesn't actually have many of the same optimizations is competitive with this state-of-the-art tool and maybe even asymptotically seems to perform a bit better. And the other lines are some of our earlier attempts that didn't scale very well. So I'll skip over that. If folks are interested, happy to talk over the coffee breaks. What I wanted to have time for was to talk about some of the work that we're currently doing to go further. So everything I've talked about is sort of work from sort of circa 2014 to 2019 or so. One thing I'm really excited about is that Netcat is this language that, to me, is very beautiful, and it's kind of remarkable that you can come up with this model that seems to fit a certain subset of what happens in a network, and it lines up so beautifully with formal language theory and automata and equational axioms and all of this. And we've used it for a bunch of stuff, and it's perhaps inspired some other work, but hasn't literally been used as designed. And about 6 months ago, some folks at Google, not people not my students, not anyone I know, were looking around at a way to verify isolation properties for their cloud networks. And reasoning about isolation was one of the examples in our first paper on Netcat. So they found this Netcat paper. And then they wrote to some of my students who are at Google and said, oh, you know about Netcat. Could this language work for us? And they've started a pretty serious effort to use Netcat to verify isolation between tenants in Google's cloud networks. In doing so, they are generalizing the language a bit because, of course, Netcat's this core calculus. It's too simple. They have to model things like tunneling protocols. They have to deal with idiosyncrasies of if the network people know about SAI and Sonic, these kind of pipelines, they have to find ways of either abstracting or encoding those functions into Netcat. But they found ways to do it, and it's Google, so they have to build it all themselves. They built a clean slate implementation based on our PLDI paper in C++, and they're starting to use it for verification. So that's kind of cool, and I'm excited to see someone using this model in anger. I'll talk about some of the other academic work we're doing and have done. So one is we've been recently looking at enriching Netcat's data model to where instead of having this simplistic, there's a certain set of fields and that's all you get, instead, a packet is what a packet really is. It's just bits. And when you want to look into these bits, you have to access it in some disciplined way. So you can sort of look as deep as you want into the packet, but you can't just sort of do random access over the whole packets. So we have a model we call StackCat, where we've changed the data model. So there's no more fixed set of fields. Instead, there's these push and pop operations, and then you can create fields on demand as you go. And for technical reasons that are probably obvious to some of you, we only have one stack. If you had two stacks, you'd have a Turing machine, so that would be too powerful. So we have just one stack that encodes, if you like, the packet. And this seems like a pretty natural extension. It lets us model a bunch of things like packet parsing in the style of the P4 language. We can do tunneling protocols in a more natural way. And we can do some of the in-network computation examples that I was talking about earlier, using the stack as kind of the scratch space. From a theoretical perspective, what's kind of remarkable is, although we add this stack, we actually don't get into the mess of the full complexity of pushdown machines. So this is restricted enough due to some other details of the model that program equivalence is still decidable, and we actually have been able to extend our axiomatization to handle this richer language. So that's kind of neat, and it's something we're starting to push on. We think it could actually be practically useful in the future. Another thing I'll quickly mention, actually I'm going to skip over this because I didn't really talk about verification, but I'll just say we've also looked at extending the language with probabilistic primitives, which would be useful for modeling everything from randomized algorithms that you might be running in the network for load balancing or things like gossip and epidemic protocols like Prabal was talking about yesterday, or for reasoning about quantitative performance aspects like congestion or latency or also things like resilience. And this was a little sub-project. It was Stefan Smolka's PhD, but essentially you can do that. And so it's another extension you make to Netcat. You can work out many of the same structures, and you can build tools that scale pretty well. And then you can get a reasoning tool that doesn't just tell you kind of yes/no answers about certain verification questions, but gives you quantitative answers, like packets will be delivered with some probability. And then the last thing I want to talk about briefly was lately we've been doing some work on inferring models of unknown networks. And I should have said this with the ProbNetCat work. One of the things that really inspires us is because Netcat has this foundation based on existing structures like cat and automata, it gives us some guidance as we explore these extensions. So another thing we can do is to think about taking unknown networks and then using something called active learning of automata to learn Netcat models. So if you haven't seen active learning before, it's this really beautiful idea. It comes from kind of 1980s learning theory. And there was a really famous paper by Dana Anguillan, an algorithm called L-star, where it looks like this. So basically there's sort of two players, and one player you think of being the teacher, and they have a language in mind. And then there's a so-called learner, and the learner is allowed to ask the teacher two kinds of questions. They can ask if the unknown language contains a given string, and if they have an idea for maybe what the language might be, they can give them a description of that language, such as a DFA, and the teacher will either say, yes, that's the answer, or no, it's not, and give them some counterexample. So the way this game works is the student, the learner or the student typically starts by asking a series of questions. Maybe is the empty string in the language? The teacher could say yes. Now the student starts building up some hypothesis for what the language might be. They can ask more questions. Is A in the language? Yes. Is B in the language? No. Okay, so maybe they get this automaton, and so on. And they can get all the way until they have an automaton to guess, and then they can ask, is this the language? And the teacher in this case will say, no, that's not the language I have in mind. And a counterexample is BBB. I won't show you the game going on, but you can actually, the classical result is in polynomial time, the learner can actually learn the language. So this is a just picture of that kind of setup. This is just from Anguillan's work from the 80s. We've been applying this to Netcat, exploiting the automata structure of Netcat, and there's a bunch of complexities, which I'm sorry I don't have time to show you, but I'll just show you the kind of payload. We started to apply this just in synthetic benchmarks. So we basically have an unknown network where we either have a pile of traces or we have an ability to sort of inject probes and then observe how those probes are processed by the network. And our tool is not fast at the moment, but we actually can effectively learn at different levels of abstraction Netcat models of these networks. And so we think this might be useful for a variety of things. Some folks have used this kind of active learning for doing verification or other kinds of testing, as well as just building models of maybe peer networks that we don't know their topology, we don't know their policies. So I think it's kind of another cool application of NetCat's Automata Theoretic Foundation that could be useful. Okay, I am straight out of time, so I'll stop there. Happy to talk about the stuff I skipped over in the break, but thank you again for inviting me, and I want to acknowledge NetCat's a project that's had many, many students involved, and of course they did all the real work. I just want to highlight a couple of collaborators and students and postdocs who have really done the heavy lifting. So Arjun Guha, who's now a professor at Northeastern, was a postdoc who did a lot of the work on NetCat itself and on the compiler. Jules Jacobs is a current postdoc. He's done the work on the fast verification engine that I slightly skipped over. Let's see, Mark Moeller is my current student who's working on active learning. Stefan was my former student who worked on probabilistic NetCat. And then Dexter and Alexander are my colleagues who are collaborators and conspirators on all things NetCat. Okay, so I'll stop there and maybe take a question or two. Thanks again. Yeah, so this is one of the things that where the kind of theory of active learning deviates from the practice. And so people have used active learning with real closed box systems. Generally, what they do, as you probably know, but I'll say it for everyone else, is they just run more tests. So if you have a real black box system to which you have interactive access, there's no teacher who can give you the answer, and you don't have the source code or access to a description. So what do? Well, you run tests until you have enough confidence that maybe your model is correct. So that's this. For this setup, for these graphs, we actually did give the teacher a model. So we basically synthesized a model and then allowed the teacher to answer the questions. In a real use case, though, like I want to learn the policy that my ISP has, the best you'd be able to do is some kind of probes. And so you just have to be satisfied that after some number of tests, you've learned enough. There's a bunch of interesting questions here that I think are deeper that I'm very interested in. So as you may know, another complexity is if the network has some state, or if the closed box system has some state, then it might be that the test that you did actually twiddled some state you didn't know about. And if you're trying to actually learn a finite state model like NetCat has, you kind of might want to know that you can get back to the initial state. So there was beautiful work in the 90s and 2000s on things like homing sequences for how you could get back to reset. There's also, one thing I would like to use NetCat for is to build these models which are abstractions of more complicated systems. So I build a functional model of its behavior that might over-approximate a stateful network that actually does more behaviors. And so now the question you ask gets more interesting, because now I'm not just trying to test some really large finite state model where I don't know when to stop. I'm actually trying to check in the sense of like abstract interpretation if this finite state model is a sound abstraction of a more complicated system. So there's interesting questions there that we've just started to work on. But yeah, it's a really good question. Oh, yeah. So for those who don't know, there was some really beautiful work done in the early 2000s by Boon Tao Lu and Joe Hellerstein. So Boon was a student at Berkeley at the time. He's now a professor, I think, dean at Penn, associate dean at Penn. Just a personal story. Boon was very much an inspiration for me. So Boon joined Penn right at the end of my time in grad school at Penn. And I remember his job talk was super cool. He was basically describing routing protocols in Datalog. And he worked on this. He still works on this for some definition of works on. He works on lots of things. It was just such a cool idea. And so for me, I was very inspired to see how someone could take a really beautiful theoretical idea like Datalog and apply that to distributed protocols like BGP and other routing protocols. So at some superficial level, I think there's a connection, right? We're both interested in finding declarative abstractions. I think, and there are some people who have actually come a bit closer. So there was a group at Brown that was interested in coming up with not just models of the data plane, but also models of the control plane. And you can view the control plane for these kinds of networks, which I mostly skipped over, as just another kind of state machine or another kind of process where every state of the control plane corresponds to a different netcat program. And so you can imagine, wanting some language that let you describe those things simultaneously. And the crew from Brown used Datalog. You could even go a step further, and if you wanted to model not just these software-defined networking kinds of scenarios, but examples where you have, interdomain routing or these true distributed protocols, then Boon's work would be relevant. So I think there's a lot of connections, and some people have even explored kind of putting these things together. Maybe the main difference is a lot of the work that I've done and the Brown crew and the Princeton crew was really focused on this kind of SDN paradigm, whereas Boon's work kind of predated that. He was really thinking about classical, internet designs. But I think there's a lot of similarities, and I myself was very inspired by his work.
Guarantee bandwidth, latency, etc. So are those kind of primitives could be captured by the language?
Yeah, so I'll give a qualified yes. So some of the material that I skipped over in the probabilistic section does get into these quantitative aspects. However, we deliberately did not model things like queuing. So we were basically abstracting, having an abstract performance model where we were sort of, idealized or assuming that there's no queuing, and then computing how much load is sloshing through this network. I think we were scared and maybe inappropriately so of reinventing network calculus, which is very complicated and has some negative results. So first answer, yes, you can extend this and start to reason about performance. There is, I think, a real limitation though, which is once you get into modeling state on the devices, whether it's meters or whether it's queues or other kinds of buffers, now your semantics is going to need to capture the possibility of interaction and interference and involving multiple packets. And so you can do that, and people have started to do that. So in the SIGCOMM community, Venkat Arun and my former postdoc, Mina Urashlu, they're working on these kinds of models, but they're just much more complicated. So I think the theory is going to be a little bit less beautiful. The tools will be less scalable, but you'll be able to model and reason about these kinds of things. I'm a little bit pessimistic that trying to be so detailed about modeling the hardware level primitives that are affecting performance will lead to kind of good reasoning and good tools. I suspect that what will work is to have some kind of abstraction that is maybe slightly imprecise, but simple enough to work. And so I've not started working on this, but that's the approach that I would take. But